Hey everybody, welcome back to another round of engineering, and yeah, let's get at it. Shorter video right now just to highlight some of the reading aspects that are particularly important. So for lack of a better title, I guess I'll just call this the terminology slash notation slash review. Okay. So there we go. And this is just based off of some of those ideas that were presented in the latter half of chapter 1, the beginning parts of chapter 2. They don't really seem to fit in very well. I guess I could kind of squeeze them in as we're going through, but I thought that it might just be better to have a separate short standalone video highlighting some of the ideas. So one of the first things that I noticed that I need to point out to you, and I will be particularly bad about this. I already know just because I swap them all the time, but I'll highlight it. I'll put I versus I, and actually in here I'll also put versus J. Okay. Okay. So the convention used by our book is that uppercase I represents a constant, and I'll be more specific. I'll say does not vary in time. Okay. So our book uses uppercase I to represent a current which does not vary in time. So you might see something like Ohm's law written as V equals IR. Uppercase I does not vary in time. And in fact, I'll also put uppercase V, again, does not vary in time. So the book uses the uppercase I and V as these time-independent quantities, which means in contrast, you can immediately get an idea if I write something like lowercase v is equal to lowercase I times r. Rather than thinking of time-independent quantities, I now have time-dependent quantities. I guess more formally, I should write it as something like v of t equals I of t times r. But again, I'm lazy. Engineers are lazy. Why write extra letters? We'll just have this convention instead. So I'll try to be disciplined about that, but please give me a little bit of grace, I guess is the best way to say it, in case I accidentally screw that up. Okay. So that being said, also keep your thinking hat on, right? You should be able to know from the context whether it's a time varying current or not. Okay. And sometimes you will see it where the time varying current, and I'll write it explicitly as a function of time here. Sometimes you will see it as, something like this maybe. And again, notice that I've used the uppercase I to represent some time independent amplitude multiplied by the time varying piece. Now I also mentioned J here. Okay. And you will see this happen fairly frequently, is that because lowercase I has been reserved for a time varying current, we will use lowercase j to represent the imaginary number. Okay. Or if you're not familiar with that, we'll say j will be defined as the square root of -1. So again, you have to be careful about that. If you open up a mathematics textbook, chances are that they will use I as the imaginary number. In fact, your calculator does this as well. Okay. We are in physics. I should say physics, you tend to see both. Sometimes you'll see J, sometimes you'll see I. In this engineering and electrical engineering, J is the imaginary number. So be aware of that. Depending on who you're talking to, what field you're dealing with, you will see this change. Okay? For this class, J is the imaginary number. Okay? Good. I want to use the video to discuss is the terminology, and specifically circuit terminology. Circuit terminology. Now, you've already read this in your book. I'm just highlighting again, simply because I will be using some of these terms as we move forward in the class. Okay. So the first one would be what's called a node. Node. And a node is simply where two wires meet. Okay. Meeting point of two wires. Point of, I guess I'll put two. You guess you could put or more wires. So again, if I draw a circuit, I guess we'll put, something like right here. Yeah, let's just do something like this, like we've had. Like that. Okay. You could think of, if we said, okay, well, actually, take a minute, identify nodes. Okay, good. So you have a node right here, right? You could think of each of these. Actually, I'm going to stretch this. I guess you could think of each of these as being a different node. I guess I'll put it right here. Now, there is something that's associated with a node. It's sometimes called an essential node. Node. Or your book, I've seen it called an essential node. I think that your book uses the term extraordinary node. Okay. And this is the meeting point of three or more wires. You say, well, why the distinction? Imagine for a moment that you have, we'll do a slightly simpler circuit. Let's say you have a battery, one resistor, a second resistor, and it goes back to the battery. Okay. Technically, what we have here is that we have one node right here, somewhere in that line, right, connecting between the battery and the first resistor. We have a second node somewhere right here, connecting the first resistor and the second resistor. And then we have a third node, I'll put it right here, connecting the second resistor back to the battery. So technically, in this bottom figure, we have three nodes. But you'll notice that all of those nodes, we have 0 essential nodes. So I guess a different way to think about it is an essential node is a location where there is a possibility of the current splitting. It actually gives multiple paths for the current to go. So that would be a way of identifying an essential node. Can the current actually split, or is all of the current have to go down the same line? So that's the first term. Good. Second term is what we call a branch. And a branch is a path, say path in circuit containing one circuit element. And maybe I should be more specific. I'll say a path between two nodes. two nodes containing one circuit element. So if I go back to our simplified drawing, we said, hey, there's a node right here. Actually, let me do that in green or some different color just so that we can see it. You know, there's some node right here, some connection point here, some connection point there. Okay. And so in terms of branches, we again have 3 branches. One branch right here containing just the battery, a second branch containing the first resistor and the second resistor. Now, if we go to the slightly more complicated circuit that I had drawn earlier, I think we had something like, excuse me, now I've forgotten. Okay, so now we have something like this. Go ahead. How many branches? Yeah. Well, let's go ahead. I'll mark the nodes again in purple. So we have another node here. We have another node there. Okay, so we still have 3 nodes. Okay. But now we notice that, okay, well, we go, since we have 4 circuit elements, we better have 4 branches. Right. So we have branch number 1 right here. We have a second branch containing that resistor, the third branch containing this resistor, and the fourth branch containing the battery. Now, just like how we have nodes and essential nodes, okay, there are things called branches and then essential branches. Branches. Or again, you could use branch, oh boy, I can't spell. Or again, you could use the idea of extraordinary. Okay. And the idea is no different. The only thing that we're going to change is that an essential branch is a branch between 2 essential nodes. So we'll say branch between 2 essential nodes. So go ahead, this first circuit, how many essential branches? None. Good. Right? There are no essential nodes, so there are 0 essential branches. How about the bottom circuit? Okay. Here we have to be careful. If I'm not mistaken, okay. So how many essential branches? Well, we have 1 essential node here. We have a second essential node there, right? 3 wires in, each one leading to a different circuit element. 3 wires in, each one leading to a different circuit element. So, okay, well, this one is clearly an essential branch. There's 1. A second one would be here. And a third one is this way. Maybe you caught that. So it turns out there are 4 branches, but there are 3 essential branches. Okay. Good so far? Okay, good. I just want to make sure on terminology. Last one, and then we'll call it quits for the video. So the last term that I'm going to give you is what I call a loop. Okay? Now, a formal definition would be what we call a path. I'll say a path through circuit starting and ending on the same node. Say starting and ending on the same node. Okay. And it has a very special thing though. Without okay, double crossing or without passing through any node more than once. And I'll highlight more than once. The idea being that you can go through a node either 0 times or 1 time, but no more than 1 time. So what that does is that prevents you from doubling back. Okay. So the more complicated circuit, for example, draw this in again. You couldn't do something like a figure 8. So let me highlight. You couldn't do something like, okay, well, I'll go this way and I'll go down and then I'll come around and come back up and then go through and come back down and come back around. Okay, that's a no-no, right? Because I did that figure 8, that it requires me to pass through a couple of nodes several times. That's a oh, nay, nay. Do not do that. So the figure 8 would not be a valid loop. Okay. Whereas something like, and we've used this a lot, so it probably rings a bell, something like starting with the battery and going all the way around outside and coming back, you notice that I don't pass through any node more than once, and so that's a valid loop. So just like nodes, where we have the node and then the essential node, or branches and essential branches, there are very special types of loops, which are usually referred to as a mesh. So this is a very special type of loop, and I'll say it is a loop which does not contain, and I'll put contain, maybe in parentheses, I'll put surround, another loop. Or if you want a different way to think about this, I'll say smallest, and notice I put it in quotes, smallest possible loop. So to give you an idea, a demonstration idea, let's say I take this outer loop again. If I consider that outer loop around the circuit, is that also a mesh? Survey says no. Okay. You notice how this outside loop right here actually surrounds a smaller loop. Namely, I'll do that one in green, surrounds 2 smaller loops, one right here and a second one right here. Okay. So the outside loop is not a mesh. However, those 2 that I had in green, which I shamefully already got rid of, each of these would be considered a loop and a mesh. You notice that the one that I've done here, actually, I guess I'll do it like this, that does not contain any smaller loop inside of it. So that would indeed be a mesh. Same thing, this one would also be a mesh. There is no smaller loop contained within it. So keep thinking about that. Okay, we give you these terms not to make your brain spin, and hopefully some of them make some intuitive sense already. I don't give these to you make your brain spin, but rather because they can be helpful when describing a circuit and also determining how many equations you need. So for example, next video, when I want to apply Kirchhoff's current law, KCL, Kirchhoff's current law, I can do that a specific number of times. Well, how many times? If I count up the number of essential nodes, I can apply Kirchhoff's current law this many times. So if I have 2 essential nodes, I can apply Kirchhoff's current law once, 2 minus 1. So that's the first thing. If I have the number of essential nodes, I know how many times I can apply Kirchhoff's current law. So that's why that terminology comes in. The mesh comes into play when we start talking about one of our methods of solving circuits a little bit faster. Same thing with the node. So there's some actual practicality behind some of that terminology. Last thing, in terms of symbols, circuit symbols that you're going to need to know as we start moving forward rather quickly. Now, I assume that you're familiar and remember things like, I've already used them, batteries or resistors, capacitors, and inductors. So I assume that these at least ring a bell. If you didn't remember them, when I use them, hopefully they ring a bell, jog a memory. Now, there are a couple of new symbols that will very quickly start being used, both in your textbook, and I'll start incorporating them into my lectures as well. Okay. One of them is what is called the independent supplies. And with contrast, I'll put the dependent supplies. Okay. So you have what are called independent sources. Maybe I shouldn't say supplies, I'll say sources. That might be a better, excuse me. I was thinking power supply or voltage supply. I should say sources. So you have independent sources and you have dependent sources. An independent source, how we represent that is with a circle. It'll be a circuit element with a circle. A dependent source, rather than using a circle, it will be a diamond. I know this sounds confusing right now. It will hopefully make more sense as you see them more frequently. So you have independent sources, okay? Sources that keep providing a constant potential, for example, regardless of what else is going on in the circuit. In fact, an independent potential source, we note that by having a positive and negative sign. This would be an independent voltage supply. Conversely, if we wanted an independent current supply, independent, so we use a circle, and then current, rather than using the plus minus, we use an arrow. So this would be an independent current supply. And again, notice the direction of the arrow is giving you the direction that the current is flowing. Similarly, the plus minus gives you which side is the high potential side and the low potential side. So for the dependent sources, I already said that you will have some sort of diamond. And how do you think you represent a dependent voltage source? Yeah, you got it. Diamond for the dependent, but then you use the plus and minus to indicate the voltage source. How about a dependent current source? Yeah, you got it. An arrow. Good. Good. Now you say, why does it depend on? Generally, you can start building circuits where a potential difference across a source depends on some other part of the circuit. So if you will, these dependent sources start building in feedback mechanisms from other parts of the circuit. And I don't have good examples for you right now, but you could see where that could potentially be helpful. Hey, if there's this kind of current in that part of the circuit, shut this part of the circuit down, for example. There's 4 different combinations, and anytime you see a dependent source, there will also be some sort of equation giving you the current as a function of something else, or the potential as a function of something else. And there's 4 main types of dependent sources. There would be the current controlled voltage source, the current controlled current source, and you can see the combinations now, the voltage controlled voltage source, and the voltage controlled current source. Okay. So there's 4 possible combinations. Is it a voltage supply or a current supply? That would be the latter 2 letters. And what is doing the controlling? Is it a voltage source or a current source? So there's the 4 combinations there. Don't worry, we'll walk through it in the examples and it'll hopefully start becoming clear. So I apologize, this video ended up a little bit longer than I anticipated. I'll try to hack through it and hash it down a little bit. But that's, I believe, all of the terminology that you need to know to move forward and be successful. Thanks for your attention. I'll see you next time.